for our different gas laws, this is all section 3, starting with Boyle's law. Boyle's law relates pressure and volume. Basically, as one increases, the other one goes down. They're inversely proportional. And just a reminder that pressure is caused by gas particles or really anything hitting container walls or hitting each other. And as volume, let me get a pen here. It's writing a different color today since we got the whole crayon thing going on here. Let's do some neat. So over here you can see that as the volume goes down, these little gas particles are shoved into a smaller space, and so they're going to hit the walls of the container more often, which causes the pressure to go up. Flip side of that, if you expand the gas, if you give the gas more room to spread out, then the gas particles are going to run into the wall less often, so the pressure goes down. And there's a nice little picture of Boyle for you. So this is what Boyle's law specifically states. And if I were to ask you what kind of graph is volume versus pressure, well, since they are inversely proportional, that means our graph is going to have a negative slope. Come on. There we go. And here is the formula for Boyle's law. The first pressure times this first volume is equal to the second pressure times the second volume. And this little picture that I have over here, this is a picture of two balloons that are connected by a hollow tube. They were both inflated just a little bit, and if you were to take one of the balloons and put them underwater a little ways, like if you were to actually make this contraption and stick one end of it in your pool, then this balloon, because the pressure of the water is going to be pushing in on the balloon like that, then it's going to cause the balloon to shrink a little bit, which then pushes the air up through the little hollow tube into this balloon, which makes it bigger. So this is an actual picture of Boyle's law. You notice that this line, it is a curved line, and it will never actually pass the y-axis or the x-axis. And it makes sense if you think about it, because you can't have a negative pressure and you can't have a negative volume. It's just not possible. So here's a Boyle's law example. I'm going to show you how to work this example out using what the physics teachers here call the guess method. And I want you to work out all of your questions using this method. It seems a little tedious and it's going to take a while, but in the long run it'll help you, because it'll help you keep all of your information straight. And this is what your physics teachers are going to expect you to do next year. So what does guess stand for? Guess stands for given. Write out what you were given. Identify your unknown. Write your equation. Solved for the unknown, and then substitute in your given numbers and solve. So this is what I want you to do on every single one of these questions that we do that has variables on it. So the way that you know that you're dealing with Boyle's law is this phrase right here, constant temperature. So that tells me that I'm going to use P1 V1 equals P2 V2. So I'm going to write that out over here. P1 equals V1 equals P2 equals V2 equals. This is going to take care of the G and the U, the given and the unknown. So P1 is equal to, I need to go back up to my question. I got a number here, 1.53 liters. 5.6 times 10 to the 3 PA, pascals, PA's pascals, and 1.5 times 10 to the 4 pascals. So my first pressure was, the first pressure I got to, 5.6 times 10 to the 3rd pascals. My first volume was right up here, 1.53 liters. My second pressure was the second pressure written, 1.5 E4 pascals. And my second volume right here, what will be the new volume? So my second volume is X. So that means I need to rearrange this equation to solve for V2. So all I got to do to rearrange this equation, divide both sides by P2, sorry. Divide both sides by P2. My P2s will cancel out, leaving behind just V2. So V2 is equal to P1 V1 over P2. So now I just substitute in my numbers. P1 was 5.6 times 10 to the 3rd times V1 of 1.53. divided by P2, which is 1.5 times 10 to the 4. Now, before we even solve this, think about what you expect to happen to the volume. The pressure changed from 5.6 times 10 to the 3rd to 1.5 times 10 to the 4. So our pressure went up. So that means our volume has to go down. So I should expect something that's smaller than 1.53 liters. So 5.6 times 10 to the 3rd times 1.53 divided by 1.5 times 10 to the 4. And I end up with 0.57. Let's see, we're only allowed 2 sig figs. That's a 7. Wow, my brain is not working today. 0.57, and since this is my volume, my units are liters. You can see that worked out there. All right, Charles's law relates volume and temperature, and it very logically says that if you keep pressure constant and you heat a gas, then it's going to expand. And the reason for that is that as the temperature increases, the gas molecules are moving a lot faster, they collide with the walls more often, and in order to keep that pressure constant, then the gas particles have to spread out. So another little problem that they ran into was that if they use the Celsius scale has negative numbers, and so you can't do that. So Lord Kelvin solved that little problem right there by coming up with his very own temperature scale. He was able to extrapolate data, some experiment that he did, I don't know what it was, to figure out that theoretically the lowest temperature possible is negative 273.15 degrees Celsius. This is the temperature at which there is no heat left. You can't remove any more heat, so this probably is the lowest temperature. You got to remember, cold is the absence of heat. There's no such thing as cold. You got to remember that whole thing. And so this is how you convert from Kelvin to Celsius. You need to know how to do this. I'm not really too concerned that, you deal with the 0.15. That's not that important yet. It will be later, but for right now, 273 is fine. So that's what Charles's law specifically states. Because they vary directly, the graph of volume versus temperature is going to be a positive correlation, so a positive slope. And this is your equation. And if you want to go ahead and remember this one as V1T2 equals V2T1, just so you get rid of the fraction stuff, that's fine. It works the same. So there's a nice little picture of Charles and his graph. Very linear relationship between volume and Kelvin temperature, so yay. So here's our Charles's law example. We're going to solve this again using the guess method, and that looks like this. Sample volume of gas, 15 degrees Celsius, 1 atmosphere of pressure, has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? So you can see right here that the pressure did not change. So when we have a constant pressure, then we're going to use V1 T1 equals V2 over T2. So now I'm going to write my stuff out. V1 equals, T1 equals, V2 equals, T2 equals. My first volume was 2.58 liters. My first temperature was 15 degrees Celsius. But remember, we can't use Celsius. We have to use Kelvin. So add 273 to that, and you get 288 Kelvin. My second volume is what I'm trying to find. My second temperature was 38 degrees Celsius. Again, we can't use Celsius, so this converts to 311 Kelvin. So now I need to rearrange this guy to solve for V2. So I'm just going to multiply both sides by T2. T2's cancel out. So I end up with V2 equals V1 T2 over T1. Plug in my numbers, 2.58 times T2, which was 311, divided by T1, which is 288. Plug that into your nifty little calculator. What did we do before these things? My goodness, it must have taken us forever to solve out math problems. And we end up with let's see again, we're allowed 2 sig figs, so about 2.8. This is volume, so liters. If you have any questions about these, come on in and ask. And that's all I have to say about that.